inside of these canals and semicircular canals, and most other kinds of stretch receptors at all have either secondary cells that support them, and or they have some kind of cilia extended. They're kind of specialized in that way, but generalized as well, in that they're all polarized, they're ready to fire most of the time, spend energy getting ready to fire. So if you know the basic anatomy here, that's good enough. And here's a cross-section through the cochlea. There's the vestibular canal, there's the cochlear canal, and there's the tympanic canal down below. This is a cut through, like right here. Here's the cochlea itself with a little snail shell. Here's the, if I blow it up a little bit, here's the tectoral membrane right here that sits over the, if I move that up a little bit, the organ of Corti. The organ of Corti is a bunch of cells with their cilia sticking up. They get vibrated from the fluid in the cochlear duct, the kind of salmon-colored job there. And when they vibrate, they depolarize, and you can hear different frequencies. What kind of frequency response do you think you have when you're born? From what kilohertz to what kilohertz? Can you hear 100 cycles per second? Probably not. Can you hear 20 cycles per second? Probably not. But somewhere in that range is where it starts. But it only goes to about 24,000 cycles per second. Some people can hear much higher frequencies than others. But all in all, you have different sections of the cochlea that are tuned into different frequencies. How about a dolphin or a bat? What do you think? 300,000 cycles per second? It's amazing. It's just gigantic compared to humans. So would you say we have very good hearing, or we suck at it? No, we're terrible. How about taste? Are we any good at taste compared to other primates? Nah, we suck. How about vision, however? We're really good. For primates, we're great. We do just as well as chimps, bonobos, and gorillas. We're pretty good. We're not as good as some kinds of birds, of course. They can flatten out their eyes. So, moving on. Here's a cross-section through that. So we'll use this for a quiz for the moment. What's this? The actual hearing organ is called the organ of Corti. And the cochlear canal, because this whole thing is a cochlea. Cochlear canal is where the organ of Corti sits, and here's the tectoral membrane. Not the tympanic membrane, the tectoral membrane. What's this one up on top called? I'll let you go back to here, and it's called the vestibular canal. So what's the one on the bottom called? Go back again. Tympanic. Seroscala tympanic. The tympanic canal. This is interesting. These are cochlear hairs, computer image with coloration done by the computer. And as you can see, they all have these little hair-like projections, and that's very consistent for almost all the sensory structures in humans. Not all of them, like Ruffini's and Pacinian corpuscles or lamellated corpuscles. Those things, they don't have hairs because they're actually small capsules of tissue. But anything that's elongated into a flat area, like the olfactory tissue that you're looking at, as well as the cochlea and other parts, and taste buds, all kinds of things. They're hair-like projections that get polarized, and then they're depolarized by some stimulus. Here we have the eye. So later on, when we finish this up, we're mostly starting with genetics, of course, on Monday. But just the general biology and anatomy. Here's the cornea. Here's the anterior chamber. Here's the iris. Here's the capsule with a lens on the inside. Here's the vitreous humor. Here's the ora serrata that absorbs some of the ambient light that flashes around. And here's where the optic nerve goes through from the back of the sclera, the white of the eye, sclera. So what's this section? It's above, slightly above right here. Sensory. So there's no vision here in the blind spot. This is the optic disc. There's no vision at all because there aren't any retinal cells. On the other hand, just above that, or right about there, see that dark spot right there? That's actually the area where the macula densa, and in the middle of the macula densa is called the fovea. That sound familiar? I hope. So the fovea is the area where you see most of the color. Now if you wanted to see in detail, would you look straight at something, given that there's enough light? If you want to see detail, do you look straight at something or do you look from the side? In daylight. Straight at it. You need both images. On the other hand, if it's dusk or dawn, how would you look at the image then? Because it's almost black and white. Peripheral? So you can actually turn your head. Well, the story goes that the grandpa in my family had macular degeneration. He was losing his fovea and he couldn't see straight ahead anymore. He could see from the side, as long as it wasn't at night, because he'd have to turn so far to get to the rods instead of the cones that are in the middle. The rods are at the periphery, like around the outside of this retina. And so eventually he wanted to drive into town. He lived in Galt near Stockton. Pretty much you can drive in a straight line right down the middle of the street there because there's nobody on the road. But he was starting to get dangerous, so we took his keys away from him. He insisted that he still be allowed to drive about a quarter mile from his house out to the main road so he could dump off his trash and pick up his paper. But one day, while he was driving like this, he would turn sideways, and he would turn sideways, because he couldn't see straight on anymore because the macula had degenerated. He took out 5 mailboxes because he was looking from the side. So finally we had to take his keys away from him, even for his tractor. So, is there a differential distribution of rods and cones? Are the rods directly in back and the cones are at the side, or the other way around? Cones. What's at the side, rods or cones?
Cones.
Rods. So in the middle of the eye, the most dense for detail and the best color vision is formed in the fovea, inside the macula, straight into the eye. What is astigmatism, since we did that on Monday, like the chart that we had sitting over there? What is astigmatism? Distortion in the shape or the curvature or scratches, in fact, on the cornea, like out here. Is that where astigmatism is derived? Yep. Could you cure up astigmatism by doing a LASIK or a laser kind of treatment? Can you, someone knows right now,
yep.
Can you cure up moderate astigmatism by using glasses? Yep. Can you correct nearsighted or farsightedness and astigmatism with the same pair of glasses? Yep. So, if you did the test, the Snelling eye chart, and you wear glasses, do it without your glasses and see what your corrections should be, and do it with your glasses and see if you get at least 20/20. So Lindsay did this a moment ago with her glasses. She was 20/15. If you're 20/20 at least, you don't need new glasses. But you need new glasses if it's anything other than 20/20. Should be. What are these little bones? They're inside the ear, in the middle ear.
Ossicles?
Ossicles? Yep. Name them.
Stapes, malleus.
Yep. I know it's
incus.
reviewing. So the stapes, malleus, and incus, they accentuate the vibration that comes from the tympanic membrane. And it turns out that even a moderate sound is accentuated by around 20-fold just by the curvature and the trumpet of your ear, you know, the ear hole and etc. The tympanic membrane actually accentuates another 10 or 20-fold, and the bones themselves accentuate the sound again. So the level of sound that goes to the oval window at the tip of the stapes is around 125 times magnified. So, true or false, the ear accentuates the sounds that you hear.
True.
Yep. True or false, the brain is involved in the filtration of sounds that you hear.
True.
So those guys can probably barely hear me because of this stupid thing. Can you all hear it at the moment? Yep, but you had tuned it out. And we often do that. We do filtering in everything. We can filter out on taste, smell, touch, tactile, olfactory, hearing. We filter out sounds and stimuli. And we also isolate them to accentuate them. We do lateral inhibition. We just talked about it a little bit. Lateral inhibition is information or stimulus coming from the central nervous system and turning off the sensors around the sensor that you're using, so it accentuates the feeling that you get from the sensor. It's kind of like this. If you wanted to accentuate the sensitivity in the middle of your palm, after you felt some kind of trigger, let's a spider or whatever, something like that, the central nervous system says, you know, that might be a spider. This is all slow motion, of course. That might be a spider. Maybe you better detail, understand it. Your immediate reaction might be to kill it if it was a spider. But it might also be that the central nervous system sends out neuron control around where the spider is and accentuates the touch part by nullifying the response of the cells around it. So that's called lateral inhibition. You cut down the sensory sections around something that's sensing, and that gives you better, more clear
Of where it is.
yeah, in detail, weight, temperature, etc. This is a good one and a sad one at the same time. The white, of course, is called the sclera. The yellow part around, do I have this? Yeah, I do. Probably show you this in anatomy. This part around the outside of the iris right here, that's called the limbus. And this, of course, is the iris. Here's the pupil. There are not only radial muscles, but circular muscles that open and close the pupil. If you were to go from light to dark to light to dark to light to dark, your pupil would close and open and close and open, close and open appropriately. Unfortunately, this area in the iris is sometimes very susceptible to cancer. That's eye cancer right there. That's retinal cancer. Probably going to lose that eye. Here is olfactory epithelium. We have some pretty good slides. Here is University of Kansas, I think is what this is. They do a lot of sensory stuff. Here are the hair-like cells of projections. Again, that's the consistency. It's common in a lot of the sensory structures in the body. And so these are the hair-like sensors. And what they do is they're polarized by, it costs energy to polarize them. And then some trigger makes them bend or twist or depolarize. And that sends information through. The olfactory epithelium is in the nasal cavity. And we'll see a nasovomeral kinds of tissues in a minute. Here's one that's better than the one because it's color. So if you want to, you can accentuate that part. Bladder front and back, see where the ureters are. This is all in the skin, not necessarily the organ itself. It could be you have hepatitis and you don't even know it, except you have tingling sensations on your right neck and right shoulder, like the guy facing you. It could be that you don't have a stomach problem that you know about because you're not throwing up, it's not bleeding or whatever, but you have in the middle of your back or in the middle of your chest at the xiphoid process roughly, some sections of skin that are really irritated. Ovaries, testes, all do the same thing. So you don't have to turn this in, and you didn't have to write it. But you should know at least the basics of it. Here's the retina and the back of the retina using an ophthalmoscope. These are blood vessels, of course, and here, pointing the wrong thing. These are blood vessels, of course, and here's the macula, and here's the fovea on the inside. One more time, the most detail and the best color is found in the fovea.